Hi and welcome to Physics. Hi, my name is Paul. Today I'm going to go through the answers, or at least the multiple choice answers, of the HSC Physics paper for 2020. Now, I'm not going to go through them really quickly by just giving you the answers. I'm also giving you the explanations so that if you are preparing for future exams, then hopefully this can also be as a tool for helping you remember the various concepts within the physics syllabus. So let's get started. Question number one. Question one deals with a question relating to Module 7, which is really about the nature of light. Now, in this case, we have a question that talks about a model of light to explain refraction as light passes from one medium into the other, and you have these characteristic wavelets. So this is demonstrating a wave nature of light, or the wave model of light. Now, in the 17th century, there was a battle between Newton and Christian Huygens about the nature of light. It was Newton who had the corpuscular understanding, it was Huygens who had the wave-like understanding, and so as a result, who proposed this model? The answer is Huygens. The answer is D. And now we get to question 2, which is about induction motors, which is in the unit of electromagnetism, which is module 6. And now let's have a look at question number 2, which is about induction motors. And in this case, we're asking, what are the things that are not needed for an induction motor? Now, a quick review of an induction motor is that you have a squirrel cage which rotates in a rotating magnetic field, and that rotating magnetic field will induce EMF, which as a result produces eddy currents within the squirrel cage, and they then experience a force due to the fact that they're in a magnetic field. The big thing about induction motors is that you do not need brushes for them because the central rotor can actually spin freely. Because it's an induction motor, there are a couple of things, of course, that are necessary. So let's attack this question by saying, well, what are the things that are required? In other words, they're going to be our wrong responses. So the first wrong response is B. You need a stator winding. And secondly, you do need magnetic field. I've already established the fact that they don't need a brush to work. So in one sense, our A becomes our correct response. That leaves us with D, and there's a slight problem with this particular response because in essence, although we have a current in the squirrel cage, we're not actually applying a current directly speaking. Now, the fact is that we don't normally apply currents. We apply an EMF or apply a voltage, and therefore that results in a current being produced. Now, that's not necessarily correct in this case. So we're not really applying a current. So one could be forgiven that D is a possible response. So unfortunately, this question isn't the most perfect question, but A in this case, being question number 2, is going to be an easy question. So as a result, I think A is still your strongest response. For question number 3, what is the basis for Maxwell's prediction of the velocity of electromagnetic waves? Well, in terms of Maxwell, hopefully you understand that his big claim to fame is the unification of electricity and magnetism by combining his 4 formulas, or the 4 formulas. As a result, he generated the idea of the electromagnetism, and that was alternating electric fields and magnetic fields that were self-propagating, and they traveled at the speed of light. So given that is the nature of Maxwell, clearly the only possible answer is C. Question number 4. Now we're jumping to module number 8, and in this case it's about the radioactive decay. And so we have this characteristic half-life decay rate, and we're asked for the decay constant. Now, what is the decay constant? Well, the decay constant, which we often refer as lambda, is equal to the value of natural log 2 over the half-life of the substance. Now, so all we now need to do is, when we work out natural log 2, we need to know the half-life. Well, we start at 400 right here, and a half-life is when we get half left. So that is basically at that point here if we follow the trend line. So you can see that the half-life, it drops from 400 to 200 in 100 years. So that's our half-life. So all I need to do is put 100 there. And if I calculate that out, I'm going to get 0.0069. And of course, that's B. Question number 5. In this case, we're dealing with projectile motion, which is part of module 5. It says, what change to the initial velocity would make the ball's time flight shorter? So our classic projectile motion has an object that goes under a parabola. And of course, we have a velocity that is in this direction, and of course, a velocity in this direction. So this is our initial velocity in the y and our initial velocity in the x. The whole point of parabolic motion is that this is constant and does not change. This one changes due to the acceleration due to gravity, and it is this one that determines the time of flight. So in answering this question, you'll notice that we're only allowed to change one thing. If I increase only the horizontal velocity or decrease the horizontal velocity, this is unaffected, but this is what determines the time. So therefore, this is not going to be our answers. So really, changing the vertical velocity is going to change the time. Now, we want to make the time shorter. That means we don't want it to be in the air for a significant amount of time. Now, mathematically, basically means since the final velocity is going to be, let's say, 0, that'll be half the time, so to speak. We have v equals u plus at, then really, if you want to make this shorter, then because that's going to be 0 just to get to the half point, then u has to be smaller as well. So therefore, B is our answer. Question number 6. The Hertzsprung-Russell diagram shows characteristics of stars in a globular cluster 100 light years in a diameter and 27,000 light years from Earth. And the stars are plotted on the Hertzsprung-Russell diagram and have approximately the same now. Is it age, color, luminosity, and mass? Now we can actually cut out two responses pretty quickly because here we have our brightness. So this is particularly bright up here. And here we have our dim stars. Now over here it says color index, but if you're understanding your Hertzsprung-Russell diagram, then we've got very hot stars over here and cooler stars. I'll say cooler because they're not cold, but at least they're lower temperatures than the ones over here. Then what we can automatically remove here is the fact that the color is not the same and the luminosity is not the same. So B and C are incorrect. That leaves us age and mass. Now, the key to this question is in the very first part. They're in the globular clusters, so they're all produced roughly around the same time. Now, if that's the case, even though we have this track over here, is that we have, let's say, the stars up here, generally speaking, will evolve faster than the stars, let's say, over here. They will evolve a little bit slower, but they're actually produced roughly around the same time. So that means their age is going to be the same. It's not mass, because generally speaking, the stars that are up here are more massive. The stars around here are less massive. Question number 7, the output of a device is shown. And here we have this classic changing sinusoidal pattern, but we only have a positive value. We don't have any negative values here. So which of these diagrams have the output as shown? Well, this is a transformer. If we have an AC supply in, we have an AC supply out. This is not AC, so therefore A is incorrect. This here, B, with a rotating magnet here, will produce a changing flux here, but because we'll have north here and then south 180 degrees later, you'll get again your characteristic sinusoidal pattern. Again, B is not the answer. This is your universal AC motor. We have slip rings here. So again, this is going to give us a similar graph to this. So C is not our answer. D will produce the shape initially, but because of the split ring commutator, it will make basically all the negative changes in the positive direction. So D is our correct answer. Question number 8 jumps back to module 8. Now module 8 here talks about some sort of radioactive decay. We are interested in here what is going from R to Q. Now if you look very carefully, we have our number of neutrons decreasing by 2. If we also look on the bottom scale, we have the number of protons also decreasing by the value of 2. So 2 protons and 2 neutrons. What is that? Well, that is helium-4, or it is also our alpha particle. So the first thing we can do is we can automatically notice that this is alpha decay. So that gives us possibly A and possibly C. The next part is, well, what is the value at 90? Well, look up your periodic table. It's thorium. So therefore, the answer is C. Number 9 sticks to module 8. Again, Bohr improved on Rutherford's model of the atom. Which observation by Bohr produced evidence supporting the improvement? Well, Bohr basically was concerned by the fact that Rutherford's model, the planetary model, where the atom spins around a nucleus, should be radiating energy according to Maxwell's laws. Now, that means it should spiral in. So what he took on board was Planck's understanding of the quantization of energy, and so that electrons existed in discrete orbits, not radiating any energy, and they will only release energy by a very specific amount, that is E equals HF, by determining by a discrete amount of, let's say, energy level to one to the other. And he used the understanding of spectral lines to support that. So the answer to that is A. Let's quickly review also why B, C, and D are incorrect. The collision of an electron and positron produced two photons. That is true, but the understanding of positron didn't happen until the early 30s by the discovery of the anti-electron or the positron by Carl Anderson in 1932. So B is incorrect. C, a small percentage of alpha particles fired at gold foil would have deflected by an angle by 990 degrees. Well, that's Rutherford's observations, not Bohr's. And D, a beam of electrons reflected from a nickel crystal produced a pattern of intensity at different angles consistent with Laker properties. Well, that's Davidson and Germer's experiments, where we're looking at the validation of the wave nature of electrons. Again, D is not the correct answer. All right, question number 10. An electron traveling in a straight line with initial velocity, u, enters a region between two charge plates in which there's an electric field causing it to travel along a path as shown. So here is a Module 6 question where we're looking at the behavior of charges in fields. Before we even look at this, let's have a look at what's happening here. You'll see that the charge plates here are not mentioned, but we can work that out. So the fact that the electron is experiencing a force in the downward direction helps us understand that the electric field is in the upward direction. Why? Because the electric field shows the lines of force that a positive test charge will experience, and this is negative. So automatically, so now let's read on. A magnetic field is then applied, causing a second electron with the same initial velocity to pass undeflected. Oh, well, it's experiencing a force downward. Now, we want a force in the upward direction because the fact is that the electron is experiencing a downward direction. So the only way you're going to do that is you're going to have to orientate your hand in such a way that your thumb goes this direction and that your palm faces in the upward direction. Well, that makes basically your fingers go towards you, so they're going out of the page like so. Now it says, which row therefore shows the direction of the electric field and the magnetic fields? Well, obviously the electric field is going towards the top of the page, and our magnetic field is going out of the page, and so therefore B is our answer. Question number 11. Consider the following nuclear reaction. The mass of the reactants is 7.02, blah, 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 blah. And the mass of the product is 7.01, blah, 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 U. What type of reaction is? Well, before we look at the responses, let's have a look at what's going on here. Clearly, it's some sort of nuclear reaction. Now, nuclear reactions are basically fusion, fission, and transmutation reactions. Now, fusion is basically the combining of smaller nucleons to produce a larger nucleon. Fission is the breaking up of larger nucleons into smaller nucleons, and everything else is pretty much a transmutation. Here we have lithium, and here we have helium. Now, lithium is heavier than helium, so this is not a case of fusion. So that's the first thing we can pick up. Secondly is the fact that we have a drop here in the mass. Well, that means you have a mass converted to energy, so therefore we have a release of energy. So what type of reaction this is? Well, we established it's not a fusion reaction. It's a transmutation reaction, but energy is released, so C is our answer. Number 12. In which of the following ways would the satellite have a greatest escape velocity from the Earth? Now, in this case, you can do the long way or you can do the short way. I'll do the long way. So understand that the escape velocity is such that the kinetic energy is always greater or equal to the gravitational potential energy. So that's going to give us G m over r. When you clean that up, you're going to get our classic escape velocity formula, which is that formula right there. Now, what is this m? This is the mass of the central planet. That is, it is our Earth. What's not there? The mass of the satellite. So this velocity value is independent of the mass. So who cares about the satellite's mass? We don't need it. The only variable we're interested in is r. Now we want the greatest escape velocity. Well, I need a small r, so therefore D is the answer. This is, by the way, module number 5. Module number 7 again. In this case, we're dealing with the quantum nature of light, and in particular, the photoelectric effect. So what we have is a frequency of light is fired at two different metals, and in both cases, we're getting emission of electrons with a certain amount of kinetic energy. How do I know that? Well, because the frequency is 8 by 10 to the power of 14, and if I plot that, you can see that both of them are above the metal's threshold frequency. Now, how much energy is released? Well, the energy or the kinetic energy of the electrons is always equal to the energy of the photon that it receives minus the work function. Now, that means basically that the photon determines each individual electron, right? So we don't actually increase the numbers of electrons, we actually increase the energy of each individual electron. So what does that mean over here? Well, if we look at the photoelectrons emitted, we are really only looking at their velocity, not about anything else. So C and D are incorrect because ultimately it releases or doesn't release if it basically exceeds the work function. Now, if we actually then interpolate up, we got 8 here, we can see the energy for Y is that level, and if we do the same thing for X, the energy for X is that level. So you can see metal X, the electrons have a greater amount of energy, but that means also have a greater velocity. So compared to the photoelectrons emitted from metal X, the ones from Y will have a lower energy, therefore a lower maximum velocity. So A is our answer. Question number 14. Two parallel wires, X and Y, each carry current I. The magnitude and direction of the force of the wires are represented by a vector of F, which is this one right here. The current in Y is then doubled and its direction is reversed. The current in YX remains unchanged. Which vector arrow represents the force on wire X after the change to the current in wire Y? So read this carefully. Okay, this is, by the way, module 6, electromagnetism, which is actually the motor effect. In this case, we have the wire currents going in the opposite direction, so they're experiencing a force in the opposite directions, like so. Now what happens is we have Y is doubled and the direction's reversed. So when this is reversed, what we now get is an attraction towards each other as a result. But it also says that Y is doubled, so it's actually going to have a greater strength. So the strength of this arrow will be larger. But remember, it's facing in, but carefully read it. It says YX. So YX will have a same size of force. It'll be bigger, but it'll be heading in the downward direction. So our C is our response. Question 15. A rocket returns to Earth for reuse after launch of satellites using its engines to make a controlled landing. The rocket, having a mass of 7,800 kilograms, is an approach to the ground, traveling horizontally at 20 meters per second. As shown in the diagram, when the engine is thrust, is changed to 90,000 newtons, and we're asked to work out the trajectory. Now, this is again module 5, but it's really about understanding the relationship of the forces. Now, let's break this down. This is moving in a direction, in that direction at 20 meters per second, and 20 meters per second is a constant velocity. Question is, what does the thrust of 90,000 newtons do? Well, the fact is that at the moment it's traveling at a constant velocity. So what that means is that the current experiences it's having at the moment of thrust is basically balancing out its weight. Now, what is its weight? The weight in this case is simply equal to 7,800 multiplied by 9.8. So when you calculate that out, you're going to get 76,440 newtons. So that's the current thrust to ensure it moves at a constant velocity horizontally. So now what's happening is it's going to be increased. So now what that means is that the rocket is still moving at 20 meters per second, but it's now got a greater value for the force. So in that case, we have a force that is, let's say, due to gravity in this case, but now what we end up having is a larger force in this case. So we get a net force in that direction, which means it will start to accelerate in that direction. But of course, it's still moving at a constant velocity. And so as a result, D is our answer. Make it really clear. This is actually an example of projectile motion because we have one motion which is still constant velocity, but we have a constant accelerated motion in the vertical perpendicular to that. So this is strictly a projectile motion problem. So here is a question from Module 8 again, where we have a nuclear reactor, and a nuclear reactor is all about controlled nuclear fission reactions, where we have neutrons fired into uranium-235, for example. They goes fissile and releases energy, but therefore we need neutrons. Now, if we remove the neutrons, we get no fission. If we allow them to go too fast, we get no fission. They have to be at the right speed. Our control rods removes them simply by dropping in. So if you take them out, you have more neutrons available. The moderator is designed to slow the neutrons down. So again, if you remove the moderator, they may speed up and actually slow the actual reaction down. And that's really what this is saying right here. And it then says a fault causes some moderator to leak out of the core. Now, what does that mean? We have a drop in moderator. Well, that means our reaction is going to go down. We're going to have a rate of nuclear reactions are going to decrease. Now we want to increase those reactions. So what do we need to do? We need to allow more neutrons to be involved. Our control rods are in a particular position to absorb neutrons. So therefore, if we raise the control rods, we have more neutrons available, which is therefore going to lead to an increase in the reaction, which is what we're after. So when we go through that, the withdrawal from the rods from the core is our correct answer. Question 17. This is Module 7 again, and Module 7 deals in this case with the understanding of the relativity related to light. So we have a thought experiment. Observer X is on a train traveling at a value of 0.95 C relative to the ground, and observer Y is standing on the side here. As observer X passes Y, the observer X sends a short light pulse towards the center. Now, fundamentally, before I even look at the responses, I sort of say, well, what do they see here? And so I understand here that the speed of light is constant for both frames of reference. Now, this person here is firing a signal over here, and this position, his position, is always going to be the same position relative to the sensor. So in other words, he'll have a certain length here that we will know exists between the sending of the pulse to the sensor. And of course, we'll also have a certain time, and that of course is both our proper length and our proper time, and it doesn't change. But what does Y see? Now remember, C is the constant for this guy, and C is constant for this woman over here. And so in this case, the pulse here will travel for her across to there, but in the meantime, that sensor has moved to here. So notice now what we have here is that our length is no longer the same. We have length contraction going on. The length that Y sees is shorter. But since C is constant, the time is also going to be different. In other words, we're going to have a different time. And in this case, because the length is shorter, the time will also be shorter. So, as a result, which statement about the light pulse is correct as observed by X on Y or Y in their respective frames of reference? Its velocity is observed by Y is 0.05 C. No, that's clearly incorrect because this light is always going to be C. X sees it travel a shorter distance to the sensor than Y. Now we've established that this distance stays the same the whole time, so B is incorrect. C. X sees it take a longer time to reach the sensor than Y. That is true because the fact is that this length is larger, so therefore this time is going to be longer. So this certainly sounds correct. Now let's look at D. Both X and Y see the travel the same distance in the same amount of time. That's incorrect on both aspects. Question number 18 again deals with Module 7, but this case we're dealing with the historical understanding of how the speed of light was determined. This particular question is actually related to an experiment by Electron conducted in the 17th century, where he determined that the speed of light is actually a finite value, and he actually determined it by actually studying the periods of I/O. Now, this question isn't exactly following Electron's experiment, but nonetheless it relates to that. let's go and see what this question is all about. Now, what this question is saying is the period can be determined by measuring the traveling of Io as it moves around from, let's say, point here to back to over here. And of course, this can be seen by looking at the eclipse from the time that the Earth moves from P1 to P2. In other words, at P1, it starts its position. At P2, it goes around and finishes its position. Now, the way you, of course, see it is because light has to travel, obviously, to and from. So, in other words, the distance that the light has to travel is this distance over here, and the distance has to travel from when it completely is this distance over here, which in this case is exactly the same. So, in other words, the period in this case has a particular value. But what if you did it from Q? Well, the distance it actually travels for the first position will be different to the distance it travels from the second position. In other words, light has to travel just a little bit further. So as a result, the period is going to be a little longer. What about the other side? Is that exactly the same thing? No, it's not, because in the first position, this is the distance measured here, and then the time delay will actually reduce it because now the distance is a little shorter. And so now you have a little shorter distance that light has to travel, and so therefore the period's going to be a little shorter. And of course at R, the distances are exactly the same. So even though light has to travel a longer distance, the fact is the difference between those two particular points will be the same. And so as a result, there's not going to be any time difference. And so as a result, if you were to ask what is the periods in relationship to each of these particular points, then Q will be the longest. P and R will be the same, and S will be the shortest, which means basically the longest period is going to be for Q, and that means B. And now we get to question number 19. So here we have a conductor PQ in a uniform magnetic field, and the conductor rotates around the P at a constant angular velocity. Now this again is a question dealing with module 6. In this case, we have a wire that is moving in a circle within a magnetic field. But the important thing to remember here is that in order to produce an EMF, we need to make sure that the vectors involving the magnetic field, the direction of motion or the velocity, and therefore the induced current are all at right angles to each other. So let's try to work out what's going on here. Let's have a look and place a single electron on our wire here, like so. If this is moving in this position in that direction, and also the magnetic field is also in that direction, then as a result, there is no EMF because they're not perpendicular to each other. So we agree here that at this position, the EMF is definitely zero. In that case, both A and C will satisfy that, and not B and D. But then let's have a look at PQ. Let's say it's in this position here. In this case, our little electron here is going to be moving in that direction, and now it is perpendicular to the magnetic field of B. That's fine. And so it will experience an electromotive force or want to move. But which way will it go? Well, in this case, it will go into the page because that would be, again, right angles to both the direction of motion and the direction of the magnetic field. But of course, the wire is going in this direction. And so as a result, there's still no EMF. Now, of course, that's true in this position and also in this position. So the answer is C. There is no EMF produced because the plane of the loop here is actually parallel to the magnetic field. This will only produce any EMF if the plane of the loop is perpendicular to the magnetic field. And lastly, question number 20, and probably always the most challenging of the multiple choice questions. And this question actually deals with two aspects. This is module 5. It deals with both circular motion and also centripetal motion. So what we're going to do is let's look at the question first. The diagram shows a smooth semicircular vertical wall with radius r. The ball is launched from a position shown with a velocity u towards the north at an angle to the horizontal. The ball follows a trajectory and the wall before landing to the ground opposite of its starting point. It does not reach the top of the wall. Which statement correctly describes the net force acting on the ball during its motion? So what I'm going to do first to help us understand is I'm going to flatten this so that you understand what's going on here. So what we're getting here, this curve, the ball is doing this, like so. Remember here, our velocity here in the horizontal direction is constant. The mere fact that this is curved in terms of its magnitude, we're not worried about its direction here, is still the same. In this case, the velocity in this direction is not constant. So what we have is an acceleration going on here in that direction. So remember this is a frictionless surface, this is a hypothetical problem here. Then if we look at it just from a projectile motion, the only force acting on this ball from this perspective is in the downward direction. And it's constant because it's due to gravity in this case. Now let's look at it from a circular perspective. So we now look at it from that curve here, and we're only, of course, inches from there to there. Now, in this case, it's experiencing a force inward, like so. But, of course, it's circular motion, so the magnitude of that vector is constant. But what is this force? Well, it's obviously our centripetal force formula, but that is actually the normal in this case. And the normal in this case is always, in the case of our diagram over here, always determined by the velocity, but it's the velocity that is at a tangent to that, which is the horizontal velocity, not the vertical velocity. And so therefore, because the velocity is constant, our normal value, at least in the magnitude wise, is also constant. And that means if we look at it from a side perspective here, we have our force acting downwards, which is this one here. We have our force going into the center over here, which I'm going to draw separately like so, going from the side direction here, which means the net force will be that particular value to sum of those two forces. But this I've established is constant, this I've established is constant, and so therefore this is also constant in terms of magnitude. So, the magnitude of the net force remains constant is the correct answer. Let's have a look at B, C, and D just to be sure. B, the direction of the net force is vertically downwards. No, it's not, because there's also the centripetal force, so that's incorrect. The direction of the net force is perpendicular to the wall. That is incorrect, because you have to allow for gravity. And finally, the magnitude of the net force reaches a minimum when the ball is at its highest point. This question is saying that the vertical component is contributing to it. That is not the case. This is your discriminator response, by the way, and this is the one that seems to be correct, but it actually is not correct, because as I've established, the normal is determined by the velocity that it is going in the horizontal component only. So A is our response. I hope that has helped you understand the 2020 Physics Multiple Choice section. Please like, share and subscribe. Put a comment down below if that's been helpful for you. My name is Paul from Physics High, and take care and bye for now.